We'll start in a while.
Sir, are you ready? Professor Dana, are you ready now? Shall we start?
I can share, right?
Yeah, we are able to hear. You want to check your slides?
Let me see.
And yeah, we are. Yeah. Right.
So you can see my.
Yes. Yes.
Yes. Okay.
Yes. Okay. Shall we start, sir? Shall we start?
Yes, you can start, please.
Good afternoon to everyone. I welcome all of you to the 39th lecture in the lecture series in Nonlinear Dynamics conducted by the Department of Nonlinear Dynamics, Bharathidasan University, with the support from RUSA 2.0. I'm happy to introduce today's speaker, Professor Syamal from NIT Durgapur, West Bengal. Professor Dana is a well-known person to the nonlinear dynamics community in India, and he is a world traveler. Since more than half of the participants are postgraduate students, I would like to read out his biodata in a very brief manner. Professor Dana was working as a chief scientist in Indian Institute of Chemical Biology, Kolkata, and retired from that institute in the year 2013. He had continued his research as a CSIR emeritus scientist in the same institute for a couple of years, and then as a UGC emeritus fellow in NIT Durgapur. Currently, he is working as a senior research scientist in NIT Durgapur. In India, very few people engaged in experimental nonlinear physics. Professor Dana is one among them. His field of research are chaos and synchronization, experimental chaos, complex systems, extreme events, and ecological networks. He won several awards and honors and guided several PhD students and mentored several postdocs. He had also organized several symposiums and workshops on dynamical systems, which helped the nonlinear dynamics community to meet each other and exchange their ideas. As some of you noticed, he is also an active participant in this lecture series. As I pointed out earlier, he travels a lot. He had visited Bharathidasan University several times and collaborated with our faculty members. With this short introduction, now I invite Professor Dana to deliver his lecture. Over to you, Professor.
Thank you, Professor Senthil Velan, for the kind introduction. So now I welcome all the students and all the participants. And I like to, as you see already the title, in the abstract mention extreme events. So extreme events is a very broad topic, interdisciplinary topic. In the abstract, I made this title to make it catchy, but I have to restrict to a limited area of extreme events because it's such a vast area you cannot really cover in a one lecture, and it's also not easy to understand from the dynamical point of view. So what I'm going to tell you is the story how the extreme events has been explored or is being explored, are being explored in dynamical models. And the reason is from there you can start with the simple models or networks or coupled system, which is my topic of talk. Therefrom, you can give an idea how the extreme events can originate in some simple models, and that can lead us to explain the phenomena what have been happening in nature possibly. So this is the target of this talk and the type of research, ongoing research on dynamical systems. So before going to the talk, I would like to mention about my collaborators who have supported me to basically to learn the subject. So I'm still learning. So last about 7 years, I have been trying to understand extreme events from experiments, from simple models. You like to know that this journey started from Bharathidasan University. So when I was really collaborating all the time with Tamil Maran. So during one of my visit, his student Leo Kingston showed me an experiment, and that shows some sort of a stable attractor. Is of course is a chaotic attractor, but occasional flickering. So I saw this in the oscilloscope. This is shown by Tamil Maran and Leo Kingston, and that was the beginnings. So, and it immediately strikes to my mind, possibly this large deviation from the really stable pattern or stable trajectory or attractor, this large deviation from this occasional large deviation might be an extreme event. And this started my journey or experiences with extreme events last 7 years. So whatever I have learned beyond that and develop my understanding, I like to share with you. So Diwakar Dasgupta is my current collaborator, and Chittaranjan was my former student. He's also supported. Pinaki also really started with me. Pinaki and Tamil Maran, we wrote the first paper on extreme event together. Then Ulrike Feudal also my co-authors. Thomas Kapitaniak, Urgen Kurz, Norbert Marwan, they joined later. And from the student front, Leo Kingston is the first. Then Arindam Mishra, my former student. Suman Shah is also my former students. Arnav Ray, Sayantan Nag Chaudhary, and Sarvendu Rakshit are from the ISI. So he is basically the first and student of Diwakar, but I also collaborate with them. And Avrup also, it's a Potsdam. So he is also a student of the Bharathidasan Physics Department, now doing PhD in Potsdam, Germany. So these are my collaborators. So let me go straight into the subject of what are extreme events. So for the students, I show you 4 pictures. So one is tsunami, another is flood, and then forest fire and drought. So these happens not very quite often. They are rare, particularly flood almost happening every year. It is more frequent than the forest fire, and drought also little bit rarer now, but flood is very common in India. But the thing is that when it is happening, the dates are happening, it's not repeating regularly. This is one characteristic feature of extreme events, which is large event, large deviation from that normal state, but they are not frequent. And tsunami is also very rare, but this is also an example of extreme events. So these are natural extreme events. There are few of the examples, not all. So these examples or the pictures will give you an idea what is really extreme events, and they are really devastating to life, devastating to infrastructure and economy. And now coming back to extreme events. So once again, I mentioned about the tsunami, floods, drought, and earthquakes. What is a tsunami? The expression of tsunami, high water wave, and that moves from one place to that flows one place to another, destroying cities, buildings, and floods is due to high rainfall. And the opposite side, drought, is a low rainfall. So extreme events, large deviation could be larger or lower, larger or smaller. And earthquakes, this is due to plate movement under the surface, under the earth surface. And we have also human-made and engineering systems like power blackout. We remember 2012 power blackout in the northern grid of India. Share market crashes, these are all extreme events, either in natural systems or engineered systems. But the first systematic study of what I found from the literature is the record of water level in the Nile River. So you can see that from the year 6600 to the current, there are fluctuations in the water level in the Nile River, and there are some large rise in the river water level in the rivers. So this is I obtained from the literature that this is the oldest record of the extreme events, and then started the statistics of extreme events. I am not an expert in statistics of extreme events, but I would like to mention, because this is an important aspect to characterize extreme events. So statistics of extreme events started from the data record, which has history from the 1935. We started with Gumbel, who gives a distribution how the extreme events or the size of events, regular size of events or extreme events, how their distributions look like. So three different class of extreme events or distributions are found. One is Gumbel distribution, which is exponential. Another is Weibull distribution, which really tells about the light tail, and the Fraser distribution, which talks about the heavy tail. I'm not going into details of the mathematical expression. So, but I will tell you, I'll show you what these three different types of distribution are really observed. With examples, I'll show you. And then I find this one in 1995, the record of the sea level at the North Sea. Why it is so recorded? Because in the left side you can see there is some submarine, and just before that there is a wall of water, sudden wall of water rised, and that flows. This is rogue waves on the sea. Many seamen have reported since long time that such rogue waves are appearing and destroying the crew and also the ships. So there was no such research, but since 1995, real record on such extreme events or rogue waves started in 1995 on the North Sea. And you can see the blue oscillation is basically still nominal. It's really fluctuating around a particular value. But one particular high amplitude value, elevation of the water level, is shown here in the red line. So this line again flows with time, with space, in space. So this is a kind of rogue wave. So this is another record in 1995 from the sea, in the North Sea. And these are records, but how the real systematic study started in the laboratory or with using a model. So this is the first example I find, which was done by Soli and his collaborator in 2007, as you see in the published in Nature. They designed an experiment with a laser, and there is a fiber. So this fiber was pushed with an external energy, and oscillation starts along this and really flows across this fiber. And how it looks like at one particular section of this fiber, that most of the time the oscillations is very nominal in the sense low amplitude in the dense red region. But then occasionally there are high amplitude intensity spikes. But these spikes are not regular. They're coming highly irregularly, and their amplitudes are also not identical. And when you look at, when you draw the distribution, or I mean histogram means you, for each size of amplitude, if you plot the count, how many times they're coming, you see that for the weaker, with the amplitude intensity by spikes which are really small, they have a high probability, and which are large, they have a gradually low probability. So this type of probability distributions tell us, okay, these extreme events are really rare. So this is about rogue waves, the first experiment in optical fiber. So the thing is that how to characterize extreme events? What are the characters of extreme events? First of all, as I tried to say since the first slide, the extreme events are nothing but a large deviation from a normal state. Large deviation from a normal state. What is the normal state? Normal state can be, like Calcutta, it is 35-degree temperature. It could be a normal day. And for Delhi, 40 is a normal temperature. For Trichy, maybe for 38 is a normal temperature. So if there is a large deviation from the normal state of a particular location or any variable or any observable, so this is the first indication of an extreme events. And then the statistical characteristics, they occur rarely. They could be recurrent when repeating like flood every year, but irregularly. One flood may be in September, another flood may be October, but they are regularly but more frequent. But there are non-recurrent extreme events are like cardiac arrest. Once a person has a cardiac arrest, he dies. If he survives, he usually doesn't have another cardiac arrest. COVID-19 is also a non-recurrent extreme event. But the question is, how large deviation originates? This is the main basic question, fundamental question we'll try to understand. And how frequent are rare or rare? How large deviation originates? If we answer this question, basically gives us an idea the dynamic origin of extreme events, basically in model. And how frequent or rare? We have to look into the statistics of extreme events. These two things I will try to explain how is systematically studied. Another important aspect is prediction. Prediction is the ultimate goal of any extreme event studies, but unfortunately, not much progress has happened so long. So I will just mention about the predictability, not discuss too much on the prediction. I will focus my talk on the dynamic origin and vis-a-vis the statistics of extremes. So we have a data records here. You can see this. You can have a data records, large amplitudes. Most of the time they are really nominally low amplitude oscillations. Occasionally they have a large amplitude spikes. And if you put a line, then some spikes are larger than this level, horizontal level. And how large they are, there we define a significant height. What is significant height? You take the mean of all the peaks, then add a plus minus, d is a constant and sigma is a standard deviation. Usually we take d is equal to 4 to 8, either 4 or 6 or 8, depending upon the system. And d is a constant. So d is a constant. And if any of this is the HS line you put here. Any event larger than HS called as the extreme events, not the other events. So this is one way of really indicating or detecting an extreme events, which are the events or any oscillation or amplitude of an oscillation. If it is larger than this threshold height, we call it extreme events. And we put a plus or minus sign. Plus if the amplitude is larger in the positive direction, negative for amplitude, large deviation in the negative side, like cold wave. So there is a negative deviation from the normal state. So plus minus is for the positive deviation and minus for the negative deviation. It happens in nature. With this definition to detect an extreme events, I come to one particular example which was done in 2011, is also an experimental semiconductor laser. Now it is with a deterministic system. You can see that a time series. This is a time series or intensity pulse of a laser with time, and all the spikes are below a limit which is called significant height. We have already learned what is extreme event, and all the peaks are below this height. And one particular peak is much larger than this significant height. So in this time series, there is only one extreme event. If you take a long run here, which is really shown here, so we can see that there are a number of such spikes. So these spikes are large spikes, which are larger than this threshold, are really recurrent. So they're coming back and forth all the irregularly. So this is a typical example of extreme events in a semiconductor laser reported in 2011. Now, What is the type of distribution then? So when there was no extreme event, that means only chaotic oscillation, all the oscillations are below this HS line, which is marked here, that the distribution look like almost Gaussian. But when there are extreme events like these situations, the distribution, there is a Gaussian trend, almost Gaussian trend of distribution for the height up to 300. That is the HS line. Beyond that, there are larger peaks which have a low probability. That means they are rarer. So we call it small, long tail type of distribution. So this is the two examples how the time series or observed variable look like when you saw the extreme events and their distribution look like here. I come to another example, which is on the microcavity laser. So it is a two-dimensional laser system, on spatial laser system, where you can see clearly that this of course, this is for the particular choice of parameter, as you see here, when the intensity are still, the height is still limited within a bound. But there are also some peaks which are larger. And if you look at the distribution, again, it is a non-Gaussian, almost Gaussian, where there is some red one are the extreme events, which are very low probability here compared to these. But for another parameter, this 1.17, you can see there are really very large peaks, occasional and rare large peaks, and which are recurrent. Then the distribution completely changed from the Gaussian distribution. It's a heavy tail. So these are for these events which are larger than the threshold height. So we can see that Gaussian distribution for the normal state or nominal state, and for this particular experiment, they observe a heavy tail. So we find two examples: statistics of extreme with a non-Gaussian low tail or light tail, and a statistics of extreme events with a heavy tail. So with this small introduction, I show all these examples to give you an idea how the extreme events look like in experiments or numerical simulations, and how the distribution appears. But now I'm really entering into the mechanism or origin of extreme events in a simple system. So start with a bifurcation diagram. This is a typical bifurcation diagram. All the students of dynamical system know. Take any system, either Rosler oscillator or in a nonlinear map. If you change the parameter, then you see that first of all, it started with the Hopf bifurcation period 1, and then period 2, and period 4, period 8, and then chaos. That is the intermediate periodic window, and then again chaos. But the basic nature is that the amplitude of the dynamics slowly increasing, continuously increasing. This is the typical bifurcation diagram we observe in most of the dynamical systems, chaotic systems. But in contrast, so I put that figure here, bifurcation diagram here. On the left side, I put a bifurcation diagram from a Leonard system. I'll talk about Leonard system more detail, but you see that in the Leonard system, the bifurcation diagram again with the parameter omega, the frequency, forcing frequency, where you find the period doubling on the right side, period doubling, chaos, and then sudden large expansion of that tractor, huge expansion of that tractor. And also from the left side is the initial periodic orbit, and then sudden large expansion of that tractor. And in that case, the middle portion of this is very dense, and otherwise the large deviations are very. These points are for the large deviation, intensity pulses, or the maxima, because Y maxima of the system, they are very rare because they are really very rarer points. I'll come to the details of this bifurcation diagram once again later on. We'll see that. So this is when you study an extreme event in a dynamical system, given that particular dynamical system, if you draw the bifurcation diagram, and from the bifurcation diagram itself, we understand where there is a possibility of extreme events, where there is the starting of the extreme events are there. So bifurcation diagram tells you where it starts, the extreme event may exist extreme events where it start, but why this expansion, this side and this side? And if this is an expansion mechanism are the same, that gives us the clear idea how they originate, basically how the expansion occurs due to dynamical mechanism. And this is another example in a laser model. You can see on the right side, from the periodic orbit, sudden large expansion. And from the left side, there is a period doubling and then sudden expansion. So the question is, what is the dynamical mechanism in this side and from this side that causes this sudden large expansion of the attractor? So how such an expansion of attractor happens? Where such an expansion indicates formation extreme? Whether such expansion indicates formation extreme events? Answer give us the mechanism of the origin of extreme events. That I'm going to tell you with more details now. So before going into that, I tell you the general perception so far developed in the dynamical community about extreme events that if you have a chaotic attractor, this will be, you can draw it project it in a two-dimensional plane, and when the trajectory most of the time move around this plane. But it may happen this trajectory really come into contact with in a region where some instability region exists. What is the instability region? I will tell you more detail. So a trajectory moving around this plane in some reason, sometime come near to an instability region, it shoots out and then come back to this plane. So this shoot out appears an extreme event. This is a general perception. So the answer is that what are the possible types of instabilities? Instability occurs in different systems. They are the same. Actually, there are different type of instabilities can really exist that leads to the different type of mechanism of the origin of extreme events. It could be saddle point, it could be saddle orbit, anything. And the most of the cases, the distribution look like this. So when there is a simple chaos, this is a Gaussian type distribution, the green dashed green curve. Otherwise, it could happen like this. It deviates from the Gaussian distribution and which has a heavy tail and which could also have a light tail. So I have shown you two examples when there is only light tail and another one case is heavy tail. But it may happen that this heavy tail and light tail may exist in one particular dynamical system. And how the time evolution is showing that the most of the time the oscillation remains very small and occasionally the large spikes are coming. And these are actually expression of extreme events in the time evolution of the observable or the dynamical variable. So as I said that there are different sources of instabilities. One by one, I'm not going to read all this. So I mentioned about 8 and there could be many more. And I will come to some of them when discussing about the specific examples. So you can go through these references. You can find all the details about all this dynamical origin, dynamical behavior, to particular references you can note down here, or you can call me or write to me if you want to know about them. And then origin of extreme events in dynamical systems, basically 3 types of systems I am going to discuss. Isolated system or single systems. Then I will discuss about coupled systems and then dynamical networks. So first of all, isolated systems. So how they originate? They originate due to 4 different mechanisms. One is a crisis-induced intermittency. Another is Pomu-Manivelle intermittency. another is quasi-periodic intermittency, and the fourth one is the noise induced. These three are deterministic intermittency or deterministic instabilities, but this is stochastic instability induced by external noise. These four I will explain one by one mechanisms. So what is crisis-induced intermittency or interior crisis? So this is a typical bifurcation diagram. If you vary the control parameter and plot the maxima, if you from on the right side, if you go on changing, increasing this, then we find first of all chaos. Maybe there is a period doubling before that. It is not drawn. Part of the bifurcation diagram is drawn here. It's first of all chaos, and we focus on the periodic window. And from the chaos, the periodic window arrives by a saddle node bifurcation. Here, there is also, this is a 1, 2, and 3, period 3 window. And from the chaos, this period 3 window occurs by a saddle node bifurcation. Why saddle? This is the periodic orbit, stable periodic orbit. This is the unstable periodic orbit. They collide and they produce chaos. And from chaos to periodic orbit, they really bifurcate into a stable limit cycle and the unstable limit cycle. But this unstable limit cycle, a stable limit cycle, this one, each of them undergoes a period doubling once again, and they form a chaos. But this unstable periodic orbit collide at some point from the bifurcation diagram. And at that point, there is a large expansion of the attractor, you can see. This is interior crisis. A stable chaotic attractor collide with the unstable periodic orbit, and that leads to a large expansion of the attractor. This is crisis-induced intermittency. This is exactly happening in another two-dimensional map, complex map here. So we split into 2 dimensions. I forgot x n plus I y when it could be. There you can see the bifurcation diagram with PC, with P, if you really draw a bifurcation diagram, here it is a very low amplitude oscillation, basically it is chaotic, which is shown here. The trajectory, two-dimensional trajectory of this system shows a very stable chaotic attractor which belongs to this region beyond this, when parameter is less than PC. At this particular critical parameter P, there is a large expansion. And what it tells us about this, if you take a time evolution of this around this, you see that most of the time the oscillation remains bounded in the dense region which belongs to this one, and then occasional large negative spike where we took the mean minus 5 sigma. So these negative spikes are smaller than this threshold height. But it is a large deviation from the mean value, and which is expressed in the two-dimensional trajectory as the original chaotic attractor, but occasionally large excursion from the attractor. These shadows or clouds, very thin clouds of dots, are basically representing these peaks, because it's a Poincare map. It's a kind of Poincare map, or is a two-dimensional projection. So this is how it happens. This chaotic attractor really coexists with this 1, 2, 3, 4, 5, basically unstable period 5 orbit. For particular parameter before this PC, it is not colliding with this unstable periodic orbit. But if we tune the parameter beyond this PC, this chaotic attractor collide with this unstable period 5 orbit, and then this instability starts and this occasional large spikes originates. This is the origin of extreme events due to crisis or interior crisis. And now coming back to this linear system, force linear system, which I started first experiment with the Leo Kingston, and also I already have shown this attractor, I mean bifurcation diagram, and the basically two crucial points where the experiment starts originating, and the projection at this point of the two-dimensional projection of this x and y that shows a dense region, but occasional large excursion from this dense region. This dense region basically represents this dense region at a particular, of course, at a particular omega value. We have shown this attractor, but these occasional large, the trajectories are really spaced here. Once again, so how we study this system? Before forcing the system, this is the system when there is no external forcing. This is a Leonard system. It has an coexisting system, a dissipative system, and there is otherwise it's a conservative systems. Outside is the conservative systems. Within this homoclinic orbit, this is the dissipative system, which has three steady states. At the center origin, it is a saddle point. It has a stable manifold and unstable manifold. This is a saddle point. On the left side, there is an unstable focus. On the right side, there is a stable focus. And now you focus on the system. When you force the system with a particular frequency, there is a large expansion of attractor, which really appears as this, as I shown earlier. And if you plot the Poincare plane, then you see that these dots, particular dots, due to this chaotic attractor, we have a really attractor-like Poincare attractor here. This is, but these dots away from the attractor are really noted as this large expansion from the attractor, from the chaotic attractor. These points are meaning large excursion from the chaotic attractor. And these are shown here in the dots away from this chaotic attractor. And how they originate? This is another point. On the right side, where I show the large expansion of the attractor, here at this point, you see that before the critical point, before the large expansion, the chaotic attractor is chaotic. And this is the saddle point at the origin. And there is of course, a quasi-periodic orbit cycle is in the Poincare. So this is a very quiet chaotic attractor and far away from the saddle point. But when you tune the parameter to this critical point where the large expansion occurs, what happens? This chaotic attractor occasionally collide with this saddle point. And then you can see there are there are many cloudy dots outside, which are really large spikes. So these dense regions are reflected in this chaotic attractor, and the large spikes are really clouds of dots around these points. So this way we can you can say that when the chaotic orbit collides with a saddle point somewhere in the region, in the state space of the system, they originate occasional large events which are expressed as extreme events. So this is one kind of instability that originates extreme events in isolated system. There is a second kind of Pommu-Manivelle intermittency. This is a Pommu-Manivelle intermittency. I will explain. This is a Lorentz system for R equal to the parameter R 166. This is typically periodic orbit. When you increase the parameter, this is still there are laminar or periodic phase, but occasional turbulences or instabilities. If you go on increasing this turbulent phases increases and then fill up the whole profile of the time evolution and they originate chaos. So this is a typical Pommu-Manivelle intermittency where there are intermittent instabilities or really turbulent phase or really chaotic phase occurs in between periodic phases. And in the Leonard system, exactly so in the left hand side, there is a large expansion. And you can see that in the time series, there is a laminar phase or periodic phase, almost periodic phase, but occasional large bursts are coming, or spikes are coming, which appears as extreme events. And this is due to Pommu-Manivelle intermittency in the same system from the. And here also again, you see the chaotic attractor is down. hardly easily colliding with the saddle point also. So this is another point. This is not only, this is more complicated than Pomum-Maneville intermittency, but first of all, it happens through intermittency. This is Pomum-Maneville intermittency, the second kind of intermittency. And now we are left with two more kind of intermittency. This is quasi-periodic intermittency, and it's, what is quasi-periodic intermittency? What is quasi-periodic orbit? Quasi-periodic orbit looks like a donut. So it has two frequencies. It appears from the steady point. They form a limit cycle. Then through Nymark-Sarkar bifurcation, they appears as a quasi-periodic oscillation, which appears like a donut. If you take a cross section of this at any donut, then look like a cycle. They look like a cycle, like this one. So this is a quasi-periodic orbit. If you take a Poincare section, they appear as a closed cycle. So when you observe a quasi-periodic motion, we should take a Poincare section. If you find a closed cycle, then it's a quasi-periodic motion. If you find a single point, then it's a periodic orbit. If you find 2 points, then it's a period 2 orbits. So for the quasi-periodic motion, Poincare section of the trajectory tell us that it is a closed cycle. So this is exactly happening in G1 laser. It's a 7-dimensional model. This is mainly done by Leo Kingston once again. But the model was published in 1997, but they didn't look into details of the dynamics of the system or the parameter space. So Leo has reproduced the one particular 2-dimensional parameter bifurcation diagram. What is 2-bifurcation diagram? In a system, this one, there are 2 parameters, alpha, R, and sigma. So we keep constant one of them, sigma, and then vary alpha and R. At each point, there is a particular value, coordinate value of alpha or R, and we study the dynamics of at each point and note here. And that way, we note down the whole space and then say find that this is yellow is the periodic region, red is the quasi-periodic region, blue is the chaotic region. And when there is if we change this R value, at some point we find these extreme events, which I call as large intermittent events. And this is here. Before this point, at this juncture, at this cross point, we have a time evolution like this, where the peaks are repeating after 4 periods. So this is when take a Poincare section, we find 4 points. As I said, that period 2 will get 2 points, period 1 we will get 1 point, period 4 we will get 4 points in the Poincare section. But if we change the parameter, then we find there is oscillation which has a modulation type, amplitude modulation type, and which has reflected the Poincare section as 4 cycles. Because it's a period force, so there are 4 period cycles. And beyond that, if we change the parameter, this profile remains here, this quasi-periodic profile, but occasional large events, which are larger than a threshold. And these large spikes are really beyond this boundary. These dots are indicating these large spikes. So what happens? This is a quasi-periodic intermittency. This is different from Pomum-Maneville intermittency. Pomum-Maneville intermittency originates from periodic orbit. Here is an intermittency which originates from quasi-periodic orbit, directly from quasi-periodic, not from periodic orbit. So I classify this separately as a quasi-periodic intermittency. These also originate extreme events. Coincidentally, this particular Zeeman laser model has parameter space. We find 3 different parameter space where we observe extreme events due to 3 different kinds of instability. And you will look at this probability distribution of extreme events. Here you find this is the HS line. There is a light tail. This is also light tail for these 2 type of extreme events. But for these extreme events, there is a heavy tail of distribution of events. The 4th kind of extreme events is basically the noise induced. Here I show an example of laser system. It was presented by Alexander Pisarcik and his colleagues. It shows it's a theoretical bifurcation diagram. You can see that for a modulation frequency, when you vary this, there are period 5, period 4, period 3, and period 1. They coexist at some points. Even other chaotic orbits are really coexisting. So this is a multi-stability. There is a kind of multi-stability where you can find different orbits, different oscillatory orbits due to change in initial conditions. Remember that this is due to change of initial conditions. You are getting different attractors which coexist. That means so these orbits are really coexist. This is produced with change in initial condition, not only in the modulation frequency but also change in initial conditions. So they coexist or multi-stable, and in this particular system, Mr. Alexander tried with a different force noise, different strength of noise. When you find that, then you find that most of the time the oscillation or laser intensity remain confined with this, a type of quasi-periodic it appears, but one particular large spike appears with a period 4 due to the period 4 orbit. So this is he called as a extreme events. And he noted down, he draws the probability distribution with a strength of noise. And you find this red line is the Gaussian when there is no external chaos, basically almost or zero. And then if he increase in the noise intensity, he finds that the distribution of events really deviates from the Gaussian, and slowly from the low tail or light tail to heavy tail, there's changing it. So this kind of typical example of extended non-Gaussian distribution he observed with a noise-induced extreme events. But remember that this is happening in a multi-stable system when the attractor really hopping between different periodic orbits. Now I come to the coupled systems. I have 11, okay, I have half an hour, right? Senthil Beran? Hello?
Yes.
Okay. So now second example, the coupled systems. The most of the cases in coupled system is due to attractor bubbling near the synchronization manifold. The target of our studies of coupled systems, if you already know about all these, that students of dynamical systems, we study synchronization. So in the past, in 2003, I did an experiment with two Chuvas oscillator. One Chuvas oscillator is forcing the other Chuvas oscillator. For a particular weak coupling, we find there is a nice attractor, very confined nice attractor, which represents the phase synchronization. I'm not going into detail what is phase synchronization, but I'm telling you this indicates a phase synchronization. But what happens if we tune the coupling strength just lower than the phase synchronization limit? It happens that the attractor most of the time, of course, confined here, but occasionally bubbles out. You see that this attractor looks like here, it's very dense like this, but occasionally it bubbles out to the left side here. This is very rare because you can see that the dots are not very dense, and it is reflected in the time series. This double skull oscillation is still there. This is due to the double skull oscillations, but occasional large spikes are coming, which are nothing but this bubbling, due to this bubbling. This experiment I did in 2003 as an instability in the phase synchronization, but never really thought about it as an extreme event. But what happens in 2013, 10 years after 10 years, the group in the Maryland, they took the similar type of two unidirectionally forced oscillators and find this particular temporal evolution of the error function. Error means the difference between the two state variables of the two dynamical systems. The similar state variable, difference of the similar state variables between the two systems. And there we find this is most of the time or they remain here almost near zero, but occasionally large spikes. If you plot the 3-dimensional diagram of the trajectory, most of the time, as you see, is again a double scroll type oscillation. Most of the time when the system is synchronized and the error is zero, occasionally there is a excursion away from that plane. And this away of the plane is basically bubbling. So this bubbling, which is well known since a long time, you see that this bubbling is well known in 1994, which I observed in 2003 in experiments, but it is identified as extreme event in 2013. What is the speciality of this particular type of extreme events? Is the distribution. The earlier distribution, we talk about 3 different kinds of distribution: Gumbel, Weibull, and the Frechet, T-type of long tail, heavy tail, exponential. But here, if you plot the log of this is size of the events of the error signal and the probability distribution, it follows the power law. But when the extreme events appears, they are really give a large probability. This probability almost of the mid-range events. So this is called a Dragon King because it is a deviation from the power law. This is the power law line. So it's really largely deviates from the power law or an outlier to the power law, which is called as a Dragon King. Why Dragon King? Because it's a very strange behavior of the probability distribution like the dragon. So this is a completely different class of statistical distribution of the probability of the events during the origin of extreme events. The same thing we observe in our numerical study in a coupled neuron, but due to repulsive or inhibitory interactions. Normally, when there is the coupling strength of like this, minus 0.04, this is a repulsive interaction, 2 oscillators shows alternately appearing. You see the black and the red line, they're bursting, bunch of spikes are appearing alternatively. And when you plot the projection there, they're smooth. Either they exist in this region or this region. So this is a typically antiphase synchronization manifold or antiphase burst synchronization manifold. But if you increase a little bit the coupling strength or increase in the negative direction, repulsive strength, if you increase this from 0.04 to minus 0.07, then you find they maintain this profile, they maintain this alternate burst, this blue and the red one, but occasionally there is a coherence. 2 spikes converge here also, these spikes. When there is a large spike, basically 2 spikes of the 2 oscillations converge. One of them is here. You can see the blue and red really coherent, and it really appears as this coherent spike appears along the in-phase direction, whether the most of the time the oscillations are in antiphase or out of phase, but occasionally when they really coherent, they form a in-phase, they move along the in-phase direction. I do not know if you have an understanding of the in-phase synchronization or out-of-phase synchronization, but I cannot tell you more about this. Only when there is an in-phase solution, in-phase synchronization, they really overlap on each other. When they appear alternately, they're coming alternately, they have an antiphase synchronization manifold like this. And this type of really extreme events again show the Dragon King behavior. The left side is our numerical results and the right side of an electronic experiment. So with these coupled system examples, I come to the dynamical network. Long back in 2013 again, around that point, the activity on extreme events was too much. 2007, 2014, slowly it is decaying. But around 2013, Ulrike Fordel and her group started working on the network and to watch extreme events in a really regular graph. This is a dynamical system which is called Fujug-Nagumo or efficient system, and there is a coupling, and this coupling is adjacency metric. Basically, it is a complete graph or regular graph. So they are all to all coupled. All the oscillators are all to all coupled, and he took 101 oscillators in a globally coupled way. And what you find that he arranged a plot basically another diagram where he sees that along these directions he plot a variation of BI, the parameter. So heterogeneous. The parameter of all the nodes are not identical; they are heterogeneous, and that means they have a difference in the parameter B. And he arranged along this along the ordinate, arrange all the oscillators along this with a particular value of BI. And this is a time evolution along this. What you find that this is really very, very coherent structure, coherent lines. And here there is a large spike. This belongs to this. He overlaps all the oscillation over top of that. You find that there is a large spike here, which crosses is larger than a particular threshold. So he tells us that out of the 101 oscillators, there is a critical number of oscillators. If they fire at the same instant or coherently they fire, they create a large event. If you sum up them, if they sum up, they'll show up as a very large event. But there is a critical number of oscillators. There are coherence in some of the oscillators here, but still they do not cross the critical number of, do not excite the critical number of oscillators. So I forgot to tell you one thing. These are excitable system. Excitable system means they most of the time remain silent on the steady state. Occasionally they fire. I mean, if you push an external forcing, they will fire, but then again come back to the silent state. So this is an experiment with the excitable system that tell us that if you couple them with a heterogeneity, they will create an extreme events when a critical number of oscillators fire simultaneously. So we did an experiment in a Josephson junction or a pendulum model. This is basically represents a pendulum model. We force it with external forcing to make it chaotic. Then we have a mean field coupling, again a global coupling. I will give you detail, but I'll tell you one example for a particular choice of parameter, the dynamics. This is a temporal evolution. It shows this red one is really almost confined to a small oscillation. We showed one large spikes. If you plot in the cylindrical plane, this can be drawn phi and y. This direction is y, this direction is phi, 2 pi, phi. So if this cylindrical space, if you plot this oscillation, small oscillations is confined to this region, red region. These large spikes make a trajectory around the surface of the cylinder, and this appears at an extreme event. Now I'll tell you more detail. So what do you study that? We plot again the parameter. We've taken parameter alpha as a variation. So we arrange the number of oscillators along this with the particular value of alpha, and along this we usually change the coupling. This is again a repulsive coupling from this direction to low repulsive coupling to high repulsive coupling, and the space is really separated into 3 regions. This region is really coherent oscillation due to this. All the oscillators have a small oscillation and they are perfectly coherent. And there is a region, blue, where you show the large amplitude oscillation. But in this region, or group of oscillators, where this group of oscillators in this yellow region, you can find such occasional large spiking events. So this is again we observe in a small number of oscillators, large spiking events, which is called as extreme events. Finally, I will come to one particular example I must tell you about this. So far the dynamical networks, we observed that the nodes are connected and there is no change in time. They are static. And I come to one last example where I find that the oscillators can be mobile. Individual oscillators can be mobile, that is time varying. Their position is XY space, they're changing their positions. These yellow small circles are really mobile oscillators. They carry over them, there's some oscillator, let's say Rosler oscillators. They're moving on their head, on their back, the shoulder, they're carrying an oscillator like a child, the Rosler oscillator, and moving around in space, these small yellow circles. But there are regions, some regions, when they enter into this, they find attracted, and in some other region, they can be repelled. So there are competitive actions of regions of competition where these oscillators feel attracted, and in some region they feel repulsed, moving away from each other. So under this interaction, in the long term, if you study the synchrony, the error of the synchrony between all the collective synchrony of all these oscillators, then you find they most of the time they really synchronize this zero line, but occasionally there were large spikes like the bubbling, and the distribution also show a very, very low, beyond this significant height level, there is a low probability, very, very low probability. This is typically non-Gaussian probability. So this is a kind of time varying networks also shows up with extreme events. This is again due to attractor bubbling. So I completed my basic talk. So only I want to say a few words about prediction. First of all, this is difficult, and there is no clue about prediction of extreme events so far. But there are hopes. So that I'm telling you about the hopes. One first hope is that from the dynamical perspective, around the extreme events, if you take a long time series, and around each extreme events, you take a slot, cut a piece of time evolution and put them one top of each other. Most of the time, these oscillations look like large spiking, large oscillation, and there is no coherence. The average is zero. When they are uncorrelated, basically, then the average is zero. But near the extreme event, there is started coherence, you see. Just before that extreme event, there is a coherence. Interestingly, if we increase the sigma, a d value, m mean plus 8 sigma, the significant height, this range of this length of this coherent region increases with this standard deviation, this constant d. You see that for 4 sigma, there is a coherent region, but this is very small. We increase the threshold limit, and there is a coherent length is larger. That means rarer event has a higher probability. Then more frequent events has a lower predictability. This is one of the significant really information given in 2013 again. And I'm not going into detail, but we have confirmed this from data to machine learning. I'm not going into detail, but I'm just telling you how the machine learning does prediction. So this is a machine, the input nodes, and there is a reservoir network, and these are output nodes. Input signals are really fed into this, maybe large number of inputs, depending upon how many really extreme events, past extreme events you want to feed in. And then you really optimize the parameters of this outer layer. And then if you feed information, unknown information after the training, this is the training period, this is the prediction testing period, you feed another signal and try to match with the input signal. And if they really clearly match each other, which is poor here, but it is much better here. This is a kind of prediction, which is a future direction. Not yet really, is not too much success so far. We could see, but there is a promise that machine learning could help us make a good prediction of such complex phenomena like extreme events. With this, I really summarize. The basic summary is dynamical system beta analysis. So that means if we start with a simple dynamical system, we can develop our understanding on the basics of the origin of extreme events. In the real system is a high dimensional, so it is not difficult. It's very, very difficult to understand the mechanism, but this is a starting point. A physicist always start with a simple system to understand the complex behavior. So this is the beginning, and we made some progress. Some of the mechanism of the formation of extreme events have been discussed here in isolated, coupled, and network systems, yet many unknown. Prediction is still evading. However, the question of predictability is being addressed from the dynamical system perspective. And the promises or the future work should be guided towards the model-free database when there is no model, but we have large data from the nature, and then use machine learning approaches for the purpose of prediction. With this, I thank you for your attention. I want to show you some of the publications. So we could publish some very meaningful papers in the good journals. With that, I thank you. I come back with my directly talk to you.
Thank you, sir. Thank you.
Let me see where if I may have missed.
Now the forum is for discussion.
Yes, question. So, but I want to really answer with my mobile. That will be better.
So it's time for questions.
Yeah, you can start questioning. Yeah, no problem. Yes, please.
I have a couple of questions.
At 1 minute.
No, sir, we are not able to hear you.
Hello.
Yes.
Now,
yes. Yeah. So Sudarshan, you may rise.
Sir, I have a couple of questions. First
Yeah.
one is, you were talking about instabilities. I can understand from the dynamical system point of view. How can we correlate it with real-time extreme events like tsunami, epileptic seizures, and so on, sir? Those instabilities.
Wait again, please.
I can understand the instabilities from the dynamical point of view, sir.
Yeah.
Like interior crisis and so on. How can we correlate it to the real-time extreme events like tsunamis, epileptic seizures? What plays the role of instability there in those real extreme events?
No, it's really from the both the system you mentioned about very, very complex, right?
Okay, sir. Yes.
And the tsunami is difficult to. Tsunami, as you know, that tsunami appears due to the movement of plates. Basically starts with the movement of plates, and somewhere there is an earthquake, and that starts the instability.
Yes, sir.
So this is a basic understanding. Beyond that, we do not have knowledge how it really propagates all these things.
Okay, sir. Okay.
And the brain also, we do not exactly know how the epilepsy originates. Still, we do not have a clear idea. But some sort of instabilities. So that way, still people are working on data to understand the origin of epilepsy, how to control them, all these things. So if you want to directly relate this understanding from a simple dynamical system to those complex systems is not easy at this moment. That much I can tell you.
Okay, sir. Thank you. My next question is, sir, in most of the real-time examples, say for example, extreme floods, usually extreme floods or extreme rainfall happens amidst periodic rainfall. There will be periodic rainfall, periodic change of seasons, and suddenly there will be an extreme rainfall. It can be analogous to a regular periodic system, but in isolated systems, we come across extreme events only amidst of chaos. Why it is so, sir? Can we observe it in periodic orbit as well?
No, it cannot be periodic orbit, because you see that. So someone asked long back also the periodic floods. Floods are not periodic. Floods could be very more frequent, in the sense every year there could be flood. But if you look at these flood situations, it might appear in 2018 in Kerala, but not happening in West Bengal. Another year is happening in West Bengal. Even if it is coming back to Kerala every year, let us say, but not in the same month or same dates or same week, right?
Yes, sir.
It might be coming in the same rainy season or monsoon, but monsoon has an extended period, so it is appearing within that period, but with a change in time. Actual real time, there is the time difference. So this is not regular phenomena.
Okay, so
although look like a periodic, but it's not a periodic phenomena. Maybe quasi-periodic could be. But anyway, so this is not a periodic phenomenon. Of course, flood is not a periodic phenomenon. This is my impression. If anybody has answered, climatologist, then okay, fine. But this is my answer, understanding.
Okay, sir. Thank you, sir.
So, Dweep of Biswa, you may raise your question now.
Sir, am I audible?
Yes,
audible.
Yeah, sir. So I had a few questions. So first of all, why is multi-stable attractors a necessity for having noise-induced extreme events? So why?
No, this is not the not the only condition. This is not. It cannot be the only condition, because noise always creates instability. But so far the studies going on extreme events or experiments or numerical. So this is a typical example how the noise can induce hopping between attractors that exist in a multi-stable system. So in general, noise could really create, of course, noise always create instabilities that could lead to extreme events, but we do not have, nobody has really reported any results so far. That is, I don't mean to say that.
So the multi-stable thing, that is, so noise-induced intermittency has only been reported in multi-stable attractors, but there are different orbits depending on different conditions.
Different conditions?
Different initial conditions.
The multi-stability only exists if you can observe multi-stability if you change the initial condition. Otherwise, you cannot really, if you confine your choice of initial condition, particular small region, particular in a system with a smooth basin boundary, then if you confine to a particular region, if you know that there is a basin, if you plot the basin of a multi-stable system, there could be regions of different oscillatory periodic orbits or chaos with a smooth boundary. But there could be intermingled, very complex boundary, we intermingle within. Then if you choose a random initial point, that will give away different solutions or different periodic orbits. So this is a type of multi-stability. Here we have shown what appears to me, I do not know clearly, it appears to me this multi-stability has a smooth boundary. So period 1, period 3, period 4, 5, you can see clearly at them due to change in initial condition. So a basin must be really separated into different sub-basins of different attractors. So if we change the initial condition, they will come up with the different orbits. This is multi-stability about.
Okay, sir. So another thing, at the last you said that in machine learning, like our work should be driven towards the future, but there is a lot of data. There is no concept of a well-formed grid or network, and from that we should be able to predict extreme events. But sir, so why should not there be the concept of complicated networks, and from that we can predict, why should we try to predict extreme events from raw data without the complicated network modeling involved? Why should
So actually, about predictability, people are little bit frustrated. In a sense, if even chaotic, forget about the extreme events where you find the chaotic orbit and occasional large spikes, which I observed, which I really going to report in the future as actually is a hyper chaos in higher dimensional systems. So this is more complex than chaos. Even chaotic orbit, deterministic chaotic orbit in deterministic system is really difficult to predict. I mean, to predict the trajectory of a chaotic orbit is difficult. So for the more complex systems like a hyperchaos or these extreme events is again more difficult, which is really observed. The people are thinking about alternative ways, like the one of them is I've shown how to increase the predictability, with change in threshold height. And complex network, experiments in complex network, we have been working. Some people have worked, and we are also working on complex network. But still, we can understand the mechanism of origin of experiments in the complex network. But question of predictability, again, the same difficulty, whether it is a single system or the coupled system or complex network.
Okay, sir.
Problem remains same for any type of systems.
And sir, I have the last question is, sir, what exactly is the concept of a mobile oscillator? Sir, it's a very simple question, not related to the talk. I did not understand. So how can the patches move? Like what is
if you talk about the patches like ecological system, then it's really difficult to say. But if you say the human being, what I understand, Dibakar knows better than me. Dibakar Ghosh is no better than me, who have been working since long time on mobile network or time varying network. But so for my understanding goes, I can tell you, let us say social networking.
Yes, sir.
So today we decided that 3 of our friends will meet at a coffee house, right? Okay. So with 3 of us form a group, right? And we form a node where 3 connectivity. And another day, out of these 3, one moves out, another person joins. So this is a kind of mobile network, right? Which is moving, and then they're forming a network.
Okay, sir. Okay.
This happens also like about cars.
Okay, sir. Okay, thanks.
Syamal.
Yes.
Yeah, it's a very beautiful lecture. I really enjoyed it. I would like to comment extreme events like tsunami or rogue waves, etc.
Yeah.
They can be understood as coming from nonlinear dispersive waves. Tsunami as a solitary wave, as a soliton.
Yeah. Maybe.
As propagation. So after 2004 December 2004 tsunami, we had a conference at SINP. Anjan Kundu had organized, and so there were a lot of discussions, and a special Springer volume has also come out. And you can explain the formation and propagation of tsunamis in terms of, for example, KDV, solitary wave, soliton, and so on. So that is one possibility. And rogue waves, for example.
Yeah, of course.
Yeah, rogue waves as kind of limiting forms of breathers, different kinds of breathers. Nonlinear Schrodinger equation and so on.
Yes, exactly.
Okay. So those kind of events, extreme, they can be considered as limiting case of integrable dynamical systems.
Yes.
Yeah. So coming to this, individual chaotic dynamical systems, say, take the case of Leonard equation, forced Leonard equation.
Yeah.
when the forcing is absent, it's an integrable system.
Yeah.
So we have given exact integrals.
For a particular choice of parameters, not all the...
No, for all the parameters, for general parametric values. Gladwin, Chandrasekhar, Sendilwell, and myself, we have given exact forms. So, is it possible, what happens to these integrals under the action of forcing? In the case of standard chaos and in the case of extreme events. Probably from the point of view of how these integrals get
chaotic.
Disturbed. So that could give probably some idea on extreme events, I think. There's one possible way of looking at things in chaotic dynamical systems.
Should I answer, or this is your comment?
Yeah, the comment, and if you have any further comments on this, it would be nice.
Yeah, the thing is that you know that Niels Archimedes, they have been really working on nonlinear Schrodinger equation. Even the first experiment with the optical fiber, they reproduced the results as a row waves with a nonlinear Schrodinger equations. So this trend of research on row waves using nonlinear Schrodinger equations is really quite popular. But regarding, because I do not work on these type of systems, but since I worked on the Leonard system so much, so my observation, given the conditions alpha, beta, gamma, 3 parameter, a range of parameter, which are conditions are given in our example, there we find that there is a coexistence of dissipative and the conservative systems. There is a region of parameter.
So when the forcing is absent, it's a conservative system.
But I do not know if I made a mistake or not. But we find is a coexistence of dissipative and the conservative systems, and the examples are there. Similar type of dynamics.
It's a non-standard integral, non-standard Hamiltonian.
I see. I do not know much about this. I didn't work on that.
Yeah.
So
it's not
somehow
kinetic energy plus energy, but it's a more complicated form. Yeah.
Oh, I see. Yeah. But whatever I read from your,
Hamilton's canonical equations. Yes.
So it will be good if I meet sometime, you and Chandrasekhar sometime, because we are now time for physical meeting. I will discuss more about this possibility. But as I think, are you convinced about that the force system there is a how the chaos appears from that complex integrable system? I do not have any understanding. To be honest, I do not have studied it. I do not have looked into that system from that angle of view, what you are saying. Maybe it will be, I'll be more enlightened when I meet you personally and discuss with you about this.
Yeah. Okay, thanks. Yeah.
There is a question in the chat box.
Chat box. Why the value of D is calculating should be in the range of, this is really arbitrary. It's a good question, because this D value is really completely arbitrary. It depends upon the system. A system might have a small, the small amplitude oscillation or chaotic oscillations, and there could be occasional large amplitude. And in those cases, if you put a mean plus 4 sigma, that shows up with large events. Basically, large or small is a relative term. I mean to say that, because if there is a dry area, let us say 40 millimeter of or centimeter of rainfall can create a flood, or a very area like Calcutta, which is already surface water level is very shallow, if a small rainfall can create a flood, whereas in a dry area, it will immediately dry up. So this limit has this extreme event limit has a system to system variance, like the place to place. This is one particular example. So if you look at, say, in Trichy, 40 centimeter of water cannot make a flood, but in Calcutta immediately make a flood, because Calcutta has a shallow water level and Trichy has a very deep water level. So
but why there is an upper bound?
Upper bound, there is no upper bound too.
No, you say 8.
Yeah, it's not 8. Even you can take 10, 12, it doesn't matter. So some people say it is a super extreme, but anyway, there is no particular upper limit. But another definition is the abnormality index, where they show that if the excursion is more than twice the mean value, this is also used particularly by the people with the ocean waves they work with. But at a particular instant of time, amplitude of a particular or intensity of a particular signal is large by twice the mean value, then they consider it extreme event. So this sort of variation in the definition of extreme events are there. So this is nothing really unique definition. 4 to 8 or 4 to 12, these are not unique definition. There is some kind of arbitrariness. But what is reflected in the distribution you find, whatever you take 4 or 8, if you look at the distribution of events, there is a clear deviation from the Gaussian distribution. So it could appear as a long tail or it's a heavy tail. That indicates, okay, rarity of the events. This is also another aspect or character of the extreme events. That is independent of the threshold height. So this much I can tell you, okay. But it's a good question. I appreciate.
So are there more questions? Okay, sir. Okay, sir. I'm not getting any questions, so I would like to wind up the session.
Yeah. So last time.
I would like to conclude the session by thanking Professor Syamal Dana for giving a very beautiful lecture.
Okay. Thank you, students, for attention. Okay. And thank you, Professor Laxmanan and Senthil Velan. Okay. Okay. Bye then.
Thank you, sir. Thank you.